Today, I'm going to share with you a shocking truth. Humanity is trapped in a prison of space itself. Not a prison with walls or locks, but an invisible boundary imposed by nature, the speed of light. We're used to everything having limits. A room has walls, a city has borders, a planet has a surface. But when we look up at the sky, those rules suddenly become meaningless. The stars are light years away from us, tens, hundreds, even thousands of light years. And the speed of light, the fastest thing nature allows, stands there like a jailer. No matter how powerful a rocket we build, no matter how advanced our civilization becomes, the distances between stars don't shrink. For thousands of years, we've only moved around in a tiny corner of the Milky Way, like prisoners walking in a gigantic room without visible walls, but always feeling confined. The remarkable thing is that this prison has no bars, no locked doors, just infinite emptiness that we haven't been able to cross yet. But recently, as we've begun to understand more deeply the nature of spacetime, as technology allows us to delicately touch extremely subtle phenomena, the first signals have appeared. Small ones, but enough to make me wonder, is the door of this prison, the wall of the speed of light, starting to crack open? And since I've mentioned the space prison, I have to tell you right away something else. Something that sounds very simple, but holds almost dictatorial power over all our efforts to leave the solar system. If you want to understand why we haven't gone anywhere yet, don't look at the big ships. Don't look at Starship or the massive rockets launched every year. Look at one single equation, the Tsiolkovsky rocket equation. It's so simple that almost anyone can write it down, but it's cruel enough to chain all of human civilization to crawling speeds in the universe. The essence is this: to go faster, you need more fuel, but when you add fuel, you have to carry extra fuel to push that very fuel itself. Then to push the entire new mass, you need even more fuel, and so on, an infinite loop, a kind of weight tax that never gets waived. I often joke with my students that if you want to reach 10% the speed of light, you'll need a rocket as long as New York City. But it's really not a joke. Chemical rockets, not enough. Ion drives, too fuel efficient but way too weak. Nuclear thermal, progress, but still can't break the wall of the Tsiolkovsky equation. The problem isn't that we're lacking technology, it's that classical physics, Newtonian mechanics, has locked us into a tyranny. For every meter per second of speed you want to add, the energy cost rises exponentially. This is the tyrant of rocketry, an unforgiving law, non-negotiable, forcing every traditional spacecraft to accept mosquito-like speeds compared to the stars. And that's why if we want to escape this prison, to leave the solar system within a human lifetime, the answer can't lie in building a bigger, stronger, or more efficient rocket. No. We need a completely different path, not pushing the ship through space, but bending space-time itself so the ship travels on an entirely new route. And even if we overcome the tyranny of the rocket equation, even if we have the most advanced machines classical physics allows, one truth still stands, blocking our way like three massive stone gates, three physical barriers that have halted this entire civilization's ambition to reach the stars. And I want to tell you this clearly, it's not because we're lacking intelligence, technology, or determination. It's because the very structure of the universe has set strict limits on anyone wanting to go beyond what nature permits. The first barrier is time. Imagine this: we take the fastest ship humanity has ever built, then upgrade it tenfold, even 20-fold. Sounds powerful, right? But even then, to reach Alpha Centauri, the nearest star, we'd still take tens of thousands of years. That means an interstellar mission with traditional technology would last longer than the entire history of human agricultural civilization. A journey where your ancestors depart and their 80th generation descendants arrive. No society, no political or economic system could sustain such a project without collapsing. This is the most suffocating point. If travel time exceeds a civilization's lifespan, that civilization cannot become interstellar. The second barrier is energy. In physics, there's a cruel truth every propulsion researcher knows. To double speed, you need 4 times the energy. To triple it, 9 times. A little speed increase is easy, but reaching speeds sufficient for interstellar travel, that's an energy nightmare. Today's rockets, whether chemical, ion, plasma, or even nuclear, have all hit their physical limits. We can make them a bit more efficient, improve a few percent, but to reach near light speeds, we'd need millions of times more energy than we can produce today. And the consequence of this equation is clear. Energy scales exponentially faster than any technology based on burning something for thrust can develop. It doesn't matter if you burn hydrogen, xenon, or nuclear reactions, the price is still exponential. This is no longer an engineering problem. It's fundamental. The third and absolute barrier is the speed of light. Einstein showed that no object with mass can accelerate past the speed of light in space. To reach it, you'd need infinite energy, and no physical object could withstand infinite acceleration. This puts all of human civilization in a dilemma. We want to reach the stars, but every traditional means slams into an impenetrable wall. No matter what engine you use, ion, nuclear, antimatter, as long as you're pushing an object through space, you're bound by the light limit. And that limit doesn't negotiate, isn't flexible, doesn't give discounts to anyone. It's the universe's hard rule. We live under the power of these three walls. Time too long, energy too vast, and the speed of light inviolable. So if we rely only on engine push through space thinking, humanity will never become an interstellar civilization. All our modern technology, from chemical to electromagnetic, plasma to nuclear, is running in a long tunnel with no exit. This is something many people don't like to hear, but it's the truth. Today's rocket technology can take us to Mars, to moons, to asteroids, but it will never take us to the stars, not within a time frame a civilization can survive. And from this absolute dead end, a new question emerges. If we can't move through space fast enough, is there a way to make space move around us? If we can't exceed the speed of light by accelerating, can we go faster than light by changing the playing field itself? This is where I want to take you to the most important turning point in the story. To go faster than light, we can't win the game of space. We have to change the rules. We have to shift from thrust engines to space-time bending engines. And from here, the strangest and most beautiful journey of modern physics begins. And this is the moment we must look at one of the central figures in this story, NASA. An organization that carries the dream of reaching the stars while being bound by very earthly rules, budgets, politics, public opinion, and scientific responsibility. I often say NASA has two faces. One face for the public, always cautious, standard, by the book. And one face for physicists, where the boldest, craziest ideas, even those sounding like science fiction, are discussed very seriously. For the American public, NASA can't speak freely. They have to weigh every word, because a misspoken statement could cost them hundreds of millions in funding at the next review. The press can twist ideas, turning preliminary results into NASA has discovered warp drive, and when that's not true, the backlash is enormous. That's why NASA shields itself with familiar defensive language. You'll see them say things like, "It's still too early to conclude." The results are highly speculative. Independent verification is needed. Error cannot be ruled out. This isn't pessimism. It's a survival strategy in the American political environment. But the interesting part is this: behind that cautious language, the actual activities are completely different. Internally, research teams are receiving new curvature measurement equipment, ultra-sensitive devices originally developed for gravitational wave research. These upgrades happen continuously, never appearing in official news releases. New projects are launched, but without specific names. They're just labeled with internal codes like A23L, HPMX4, and sometimes the project names themselves are classified, known only to team members. The Advanced Propulsion Group, once just a few researchers, has tripled in size. Some of these physicists don't work publicly. Their records are listed under field dynamics, precision measurement, or novel energy patterns, harmless-sounding phrases that hide experiments related to warp metrics. I've seen some partially declassified documents. Interestingly, the declassified parts only say very ordinary things, like measuring electromagnetic fields in the test chamber. But the redacted parts, covering 60 to 70% of the pages, are right after sections mentioning space-time curvature anomaly or unexpected field deviation. You don't need to be an expert to know something important is being hidden. In NASA's internal meetings, when a team detects an unusual signal, like a tiny nanoscale distortion in space-time structure, they don't announce it right away. They send the signal to another lab for confirmation. They repeat under the same conditions, change equipment, operators, algorithms, just to ensure it's not noise. Meanwhile, public reports are written very modestly, no clear evidence found for warp-like effect. But to those who know the game, that sentence is a signal, something big enough to require repeated checks. Some documents even explicitly request accelerated warp metric simulations on supercomputers. Requests for more simulation resources never appear in public reports, but internally they're prioritized tasks. And you know, NASA never allocates more resources to a model they think is useless. There are also meetings I know of that last hours just to determine if a nanometer deviation is system error or a real phenomenon. In those discussions, no one says things like too speculative, too early. Those are for the press. Here they say, if this isn't noise, what are we looking at? And that's the question showing their seriousness. What many people don't realize is that NASA lives in a dilemma. They must be cautious to protect reputation and resources, but internally they must be bold enough to pave the way for discoveries beyond classical physics. These are opposing pressures they balance every day. So, when you see NASA silent, it doesn't mean nothing is happening. It often means too much is happening, but it can't be said. There's an unwritten rule in breakthrough research communities. The quieter, the more noteworthy. And with warp drive, NASA's silence is becoming harder to ignore. Because if you look closely, you'll see small but steady movements in the shadows. Equipment orders, lab expansions, new algorithms tested, hard to understand models quietly circulated. Behind that cautious mask, NASA is moving. And that movement, silent, slow, but determined, is bringing us closer to the boundary science once thought impossible to cross. And if you think everything is only happening in a few closed rooms at NASA, let me take you a bit further, to research centers spread across America, where a quiet network is expanding. No one calls it a warp project, but all signs point in the same direction. Glenn Research Center in Ohio is the first I want to mention. Glenn has long been the heart of traditional propulsion. Jet engines, ion drives, hybrid propulsion, but in recent years, Glenn has quietly shifted focus to research that no longer sounds like ordinary rocket science, field dynamics, energy distribution in curved spacetime, and models for evaluating force interactions when the metric is distorted. Labs once dedicated to measuring combustion chamber temperature and pressure now have added miniaturized curvature detectors devices. Once only in basic gravity research, no one publicly says what that means, but everyone in the field understands. Movement is happening. In California, Ames Research Center plays a different role. Ames is famous for supercomputers and large-scale aerodynamics simulations. But when you look at internal orders, you'll see simulation hours for nonlinear metric curvature modeling skyrocketing. Ames doesn't build hardware. Ames doesn't measure. Ames simulates. And to simulate warp metrics, you need resources only a few places on Earth can provide. Those nonlinear curved spacetime models are never labeled warp bubble simulation. Instead, they're under harmless categories like field discontinuity studies or high-energy geometry testbed. To outsiders, it looks normal, but to physicists, it's warp cavity simulation. Meanwhile, in Pasadena Jet Propulsion Laboratory, JPL handles a completely different aspect, engineering and materials. If Glenn is the brain for dynamics, Ames the mind for metric simulation, then JPL is where they answer if a warp bubble exists, what material can withstand it. Warp cavity walls face enormous energy gradients, rapidly varying curved fields, and high-energy particle flows. No ordinary material can survive. So JPL quietly researches ultralight, ultra-strong compounds, next-generation superconductors, and composites capable of dispersing field stress. These compounds are initially described as for deep space shielding, but their design exactly matches what's needed for a vehicle in a warp environment. Over in Huntsville, Alabama, Marshall Space Flight Center handles something few notice but critical to any warp structure's survival: structural integrity. When space-time curves around the ship, the interior space must remain stable, not stretched or warped. This isn't a material problem anymore. It's a physical architecture problem. How to build a structure that anchors flat space inside a distorted bubble around it. Marshall doesn't claim they're working on warp cavities. They just say they're researching stability of high-stress frames in dynamic environments. But when you look at the force models, those dynamic environments don't resemble rocket or aerodynamic forces. They resemble forces only seen where space-time is compressed and stretched. All these centers, Glenn, Ames, JPL, Marshall, each does a very small piece. No one claims their task relates to warp drive. Each has a nice, reasonable, publicly defensible excuse. Glenn says they're studying field interaction. Ames says they're running nonlinear geometry. JPL says they're optimizing materials for heat and radiation. Marshall says they're improving structural frames durability. But when you put all the pieces together, the picture becomes very clear. One center simulates curvature. One measures curvature. One designs materials to withstand curvature. One builds structures to exist in curvature. And when four NASA centers all shift toward the same topic, one never spoken aloud, I can tell you something is happening. No one publicly calls it a warp project. No press releases, no conferences, no signs saying warp drive development. But if you watch closely, you'll see a network forming. A network spanning from Ohio to California, Pasadena to Huntsville. A quiet but powerful network. A network where every signal, every upgrade, every order, every simulation points to one thing: preparation for the era of bending space-time. And sometimes the things not said are the clearest signs that history is shifting. And if NASA's quiet network expansion is enough to pique our curiosity, the story gets far more interesting when organizations no one would think involved in warp drive start entering the field. Not with loud announcements, not public projects, but with a series of subtle signals, small but weighty movements in the national security science world. First, DARPA, the agency always behind era-ahead technologies. DARPA never does anything out of mere curiosity. They care about warp for a very practical, very military reason: rapid global mobility, the ability to move forces or equipment anywhere on Earth faster than any current means. For DARPA, warp isn't fantasy or philosophy. It's a strategic capability. If there's a technique that can curve space-time structure, even minimally, not yet useful for interstellar travel, but enough to reduce inertia or fuel consumption, DARPA definitely wants to know first. Then the Air Force Research Laboratory, AAFRL. Few know that since the early 2010s, AAFRL has quietly funded field propulsion research, thrust systems not based on mass ejection, no exhaust but interaction with physical fields. Many reports from that period mention non-conventional inertial modification and space-time interaction concepts. Of course, no document used the word warp, but changed the wording, and the essence is the same. They're seeking ways to interact directly with space-time structure. And when the military enters a topic, you can be sure they're not just observing. They're checking for future strategic advantage. The U.S. Department of Energy, DOE, is a far more important player than most think. DOE controls particle accelerators, high-energy plasma facilities, and national labs capable of creating environments similar to high-energy vacuum, necessary for studying Casimir effects, vacuum fluctuations, or anything involving negative energy density. If anywhere on Earth can recreate conditions close to what a warp bubble needs, it's DOE labs. And interestingly, in the last 5 years, they've increased projects on high-field plasma confinement, vacuum nonlinearity, and zero-point field measurement. The names sound ordinary, but perfectly match fields warp research needs. When defense and energy organizations appear on the edge of a scientific field, something else always happens in parallel: national security groups, NSA, DIA, ONI, start sending people to scientific conferences. Not publicly, no name tags. But insiders always recognize them. What are they there for? Not to research physics, not to develop warp drive in some military facility, but to monitor information flow, see who's leading, who's advancing fastest, who's closest to a discovery that could shift the technological balance. And this is what I want to emphasize. These organizations aren't building warp drive, but they monitor everyone trying to understand it. They track Ames simulation progress, read redacted Glenn reports, watch Harold White presentations, check university lab imported equipment lists. Not because they want to publicize the technology, but to ensure if a breakthrough happens, America is the first to know and understand it. This is the gray area between science and national security, a rarely mentioned area but hugely influential on every breakthrough technology's direction. In that gray area, no announcements, no public reports, just silent questions. If this phenomenon is real, who controls it? If a civilian group accidentally discovers something important, who reaches them first? If bubble geometry can be reproduced, what are the strategic implications? When you see DARPA interested, AFRL watching, DOE adding experiments, and security agencies sitting quietly at the back of conference rooms, never asking questions, you know the topic has gone beyond pure science. It's entered the zone where every discovery must be weighed, not just for understanding, but for power. And when organizations no one expected step in, you start to realize this race, the race to understand how to bend spacetime, is far more serious than what the public sees. And if defense agencies entering makes the story more serious, private sector involvement changes the entire game in a very different way, bolder, freer, and especially less constrained. Because when private corporations enter a breakthrough field like warp drive, they don't worry about Congress, federal budgets, or political backlash. They only care about one thing: is it feasible? And if yes, they'll try, no permission needed, no waiting for approval, no defensive language. SpaceX is the clearest example. People usually judge the company's pioneering based only on Starship or reusable flights. But what's more notable is their job listings. In recent years, SpaceX has started recruiting experts unusual for a rocket company. Theoretical physicists specializing in superstrings, plasma confinement experts, relativity simulation engineers, nonlinear curved field equation solvers. Those aren't positions for improving methane-oxygen engines. Those are for entering field propulsion. And SpaceX's philosophy is perfectly suited to breakthrough research. If it can be done, we'll try. They don't care about ridicule or being called crazy. They were laughed at for reusable rockets. Now the world copies them. Blue Origin approaches differently. Jeff Bezos doesn't talk much about future propulsion, but he focuses on permanent infrastructure, space factories, space resource mining, orbital service stations, things you only invest in if you believe in 50 years. Space travel will far exceed chemical rockets. Blue Origin has hired many experts in superconducting materials, high-energy optics, and laser confinement, fields closely tied to laser-driven field manipulation, a potential method for activating or stabilizing metric bubbles. And if you look at traditional giants like Lockheed Martin or Northrop Grumman, you'll see something rarely mentioned. They filed patents related to field propulsion, mass modification, and even inertial dampening structures. Of course, patents don't prove they've built it, but they prove they want to stake a claim. In tech, staking a claim means we think this is feasible enough to own the legal framework before anyone else. And what catches my attention most are indirect signs, things no one says, but the perceptive notice. For example, unusual spikes in orders for low-temperature superconducting materials from commercial companies, or private labs signing contracts for very high-power laser systems, types previously only in national research facilities. Those systems can be used for many things, but also for creating energy pulses needed for field resonance experiments. And you see, when the private sector jumps in, the game changes completely. They don't report to Congress, aren't pressed by media to explain every detail, don't need NASA's defensive language. They can try the boldest ideas without fear of budget cuts or criticism. And they're the ones with the strongest motivation to turn science fiction into real technology. When SpaceX hires theoretical physicists, when Blue Origin buys high-power lasers, when Lockheed patents inertia reduction, when Northrop funds nonlinear plasma research, one thing is clear: they're not doing it to improve rockets 5% or 10%. They're preparing for an entirely different propulsion system. And if defense agencies enter to monitor, the private sector enters to actually build. That's what makes this race dangerous, exciting, and unpredictable more than any 21st century tech race. When private players decide to look straight at the stars, the prospect of a space-time bending engine shifts from "will anyone do it" to "who will do it first?" And here, after talking about rockets, the military, NASA, and private corporations, we must face a bigger truth. Warp drive is completely different from anything humanity has ever thought about travel. We're used to the idea that to go from point A to point B, you must pass through the space between. You burn fuel, create thrust, accelerate, cover the distance. That's thinking stretching back thousands of years, from the first sailboat to the Saturn V rocket. But warp drive doesn't work that way. It doesn't care how fast you move. It cares what you do to space itself. To understand this, we must return to one of the deepest ideas humans ever created: Einstein's field equations. I often explain them in one short sentence. You can remember, matter tells space-time how to curve. Space-time tells matter how to move. That means motion isn't you going yourself, but sliding along space-time's curve. And if you can shape that curve at will, you can travel without really moving. Imagine this for clarity. You're on a very long road. The only way to the end is walking. But if you grab the road and pull it toward you, you no longer need to walk. The destination comes to you. Warp drive is exactly that. It doesn't push the ship through space. It bends space-time so the destination comes closer to the ship. Inside the warp bubble, the ship is relatively stationary in local space. No violating the speed of light because it doesn't move in the usual sense. Space-time moves. That's why warp drive is completely separate from all previous propulsion tech. It's not a faster rocket, not a stronger engine. It's a different kind of technology. And this difference opens three major approaches currently researched worldwide. The first is the Alcubierre model, the original idea founding the whole warp bubble concept. Alcubierre proposed a space-time structure with contraction ahead and expansion behind, creating a wave carrying the bubble. This is the classic idea most people mention when talking warp drive. The second is the natariometric, a smarter, smoother approach. No distinct contraction-expansion, but a more stable space-time flow, reducing energy needs and making simulations much easier. This is the direction modern simulations are showing promising signals. The third, bold enough to sound like magic, is harnessing dark energy. If dark energy occupying 70% of the universe can be locally focused or controlled, it could perfectly create the negative pressure field needed for a warp bubble. No one knows if it's feasible, but it's one of the most exciting ideas, because it could turn something already everywhere into future fuel. And that's why warp drive is so different. It changes how we think about going somewhere. We no longer ask how to go faster, but how to change the playing field. Leaving traditional propulsion and entering space-time engineering, this turning point defines the rest of the story. And once we understand warp drive isn't pushing a ship through space, but reshaping space-time around it, we must start with the idea that paved the way: the Alcubierre model. This is where modern science first saw a crack in the universe's strict laws, a place Einstein didn't completely close. When Miguel Alcubierre published his model in 1994, many physicists were shocked, not because it violated physics, but because it followed physics disturbingly well. Alcubierre's idea was clear: create a space-time bubble, warp bubble, where the ship sits in a flat region, while space-time ahead contracts and behind expands. These effects combine to create a curved wave, sliding the bubble through the universe, without the ship inside accelerating conventionally. This is the signature structure: contract ahead, expand behind. The strange thing is, it doesn't violate relativity. The ship inside never exceeds light speed locally. It stays stationary relative to the bubble. No acceleration, no relativistic mass increase, no hitting the light wall. All motion happens in the space-time shell around it. In other words, you don't need to exceed light if you make light no longer the limit for your motion. But like every bold idea, the Alcubierre bubble had a huge problem, a gigantic one. It requires negative energy, and negative energy isn't something you buy at the store. It's a form of matter energy with negative pressure, which in Einstein's equations can make space-time expand oppositely. When Alcubierre calculated the energy for a ship-sized bubble, the result made the physics world laugh. More energy than the mass of the entire observable universe. A number so unrealistic, it seemed the model should stay theoretical. But the universe teaches us, don't dismiss anything just because it's hard to imagine. And that's when Harold White, a NASA physicist, stepped in. White proposed a key idea: required energy isn't fixed, but depends on bubble shape and energy distribution on its edge. Change the geometry, change the energy requirement. White refined the model, not changing Alcubierre's principle but optimizing bubble structure so negative energy drops from universe mass to imaginable. And unbelievably, just changing from a sphere to a flattened ring-shaped warp field reduced energy by orders of magnitude from absolutely absurd to still too large, but not hopeless. If Alcubierre's first step was discovering a theoretical escape, Harold White's was widening it enough for light to pass through. But what shocked the scientific community most wasn't theory, but a series of experiments White's team conducted. White Lab built nanoscale microcurvature detectors. Of course, no one expected a large warp bubble. They wanted to see if any curved cavity appeared when creating an energy field configured like Alcubierre's model. They used lasers, microcapacitors, superconductors, and ring structures to create field gradients, matching the bubble shell. And then the unexpected happened. They measured a tiny curvature signal, a nanoscale change in space-time structure, not a full warp bubble, not a sign of interstellar travel, but a signal matching Alcubierre model predictions, a signal small enough to be controversial, large enough to be impossible to ignore. When White released preliminary results, the international physics community reacted in three clear ways. Most skeptical, a few strongly opposed, and a small but crucial group asking, if this is true, what do we do next? In Germany, Japan, and some European labs, research groups started rerunning simulations under similar conditions. Some found small similar signals, others nothing. This is normal in early stages. Every new physics signal goes through a gray period where no one knows if it's noise or a new universe window opening. Meanwhile, supercomputers simulating warp geometry at Ames and other institutes started producing interesting images. Some models showed warp-like cavity structures in ring-shaped energy configurations. Exactly the geometry Harold White predicted could reduce negative energy needs. These structures were too small to see, but in simulations they appeared as curved bubbles lasting femtoseconds, enough to ignite the physics community's imagination. No one dared call it a warp bubble, but no one dared say it wasn't. And here, I want to pause to emphasize the most important thing. We've seen the first signals, small, fragile, uncertain, but shaped exactly as warp theory predicts. It's not proof, it's not interstellar travel, but it's a tiny crack in what seemed an absolute universe wall. And every scientific revolution in history, from electricity, magnetism to quantum mechanics, started with such cracks. Looking at those models, seeing a curved cavity appear exactly as Alcubierre predicted, I can't help thinking we're at a moment very similar to when Einstein saw the 1919 solar eclipse. A small signal, but potentially opening a whole new world. And if this continues, if labs worldwide consistently reproduce the effect, then for the first time in history, humanity can say, we've set foot in the opening chapter of warp drive technology, even if just a tiny dot in the universe's vast book, but enough to rewrite everything we thought about our limits. But the Alcubierre drive, though the first brick, isn't the only path. As physicists got more serious about bending space-time, another model emerged as a more practical candidate, simpler and requiring far less energy, the Natario model. If Alcubierre creates motion by contracting ahead and expanding behind, like compressing a carpet in front and stretching behind to create a wave, Netario takes a completely different approach. The Netario metric doesn't require expansion or contraction anywhere. Instead, it creates a space-time flow, a geometric flow where the warp bubble isn't pushed by contraction-expansion, but carried by the sliding motion of the metric structure itself. For visualization, imagine standing on a perfectly flat glacier. You don't push yourself forward, you stand still, and the ice surface moves beneath, taking you to the destination. No contraction ahead, no expansion behind, no major ice deformation, just surface movement. The Netario bubble works similarly. Outside space doesn't contract or expand. Instead, the metric is reorganized into a flow, allowing the bubble to slide. Because there's no large contraction-expansion region, the Netario model is more stable and, crucially, requires far less negative energy. And in warp physics, any idea reducing negative energy is a huge leap. When space-time isn't strongly stretched or compressed, required energy gradients drop significantly. This makes the Netario metric more attractive for current simulations because we can create similar conditions on computers or small experiments without unrealistic energy levels. Netario also has another advantage: smoother structure. Instead of a bubble with sharp boundaries like Alcubierre, Netario's resembles a rerouted spacetime region, like changing traffic flow to create a special lane for yourself. Space remains flat everywhere, just its flow changes. This fits what many supercomputers are simulating today. In centers like Ames and some international labs, physicists are running plasma-controlled geometry models using magnetic fields to create field distributions matching Netario flow. Plasma, with its flexibility and high magnetic sensitivity, is an ideal candidate for recreating complex flow structures Netario requires. Though plasma can't curve spacetime, it can recreate field conditions to test how spacetime flow might be activated in reality. And in those simulations, physicists have started seeing coiled field patterns, shapes similar to Netario flow, though still very small and idealized. But crucially, it matches theoretical predictions. The Netario metric also has a major advantage in bubble stability. In Alcubierre, the bubble boundary where event horizons form is extremely hard to control due to huge energy gradients. But in Netario, without extreme contraction-expansion, the boundary is naturally more stable, requires less negative energy, and avoids many extreme relativity problems Alcubierre faces. Another interesting point: Netario suggested some structures could completely eliminate negative energy if certain conditions are met. This hasn't been fully proven, but it opens the possibility of warp drive without negative energy, or at least very little. In the physics community, this is hotly debated, but also why many labs invest in Netario simulations over Alcubierre. Because if there's an easier, more stable, lower energy path, that's the one future technology will choose. And as usual, indirect signs are appearing. Many experiments use strong magnetic fields to control ring-shaped plasma, trying to create flows like Netario. Many internal reports use keywords like geometric routing or metric flow mapping, terms sounding more like computer network optimization than spacetime physics, but perfectly describing Netario bubble operation. Putting all these pieces together, simulations, plasma shaping, reduced negative energy, higher stability, we see clearly why many physicists think Netario, not Alcubierre, may be the first model to reach real experimentation. And looking at the whole picture, you'll understand why some scientists whisper, if Alcubierre opened the theory, Netario could be the first executing arm of warp technology. Slow, logical, stable, but full of promise. And then, after passing the two major paths, Alcubierre with contraction-expansion bubble and Netario with spacetime flow, we must face another candidate stranger, vaster, and more elusive than anything humans have tried to manipulate: dark energy. This isn't just a fringe physics resource, it's the component making up 70% of the entire universe. And what makes it a natural warp drive candidate is its strangest property: negative pressure. In Einstein's models, negative pressure can expand spacetime, pushing everything apart. Yes, that's exactly why the universe is accelerating its expansion. No gravity can do this. No normal energy can. Only dark energy. But interestingly, this is exactly what warp bubble models need: a region of negative pressure to expand spacetime behind the bubble, creating metric structure motion. When cosmologists calculate dark energy density in the lambda CDM model, they don't see it as floating matter, but as a spacetime property, a constant value throughout the universe. Instead of thinking dark energy as fuel, imagine it as the universe's background tension. Some scientists propose that if we adjust spacetime curvature correctly, we could activate or amplify this effect locally, a curvature resonance, making dark energy manifest stronger in a small region, like striking a string at the right frequency causes the whole string to resonate. But here's the hardest part. We have no way to create dark energy, no way to control it. It's everywhere, permeating all space, but completely out of reach for humans. Cosmology models only tell us it exists and causes expansion, not how to interact with it. Still, this doesn't stop theoretical groups from asking, if dark energy is a spacetime property and warp drive is spacetime manipulation, can the two intersect? Some models show that in regions of extremely high curvature, effects similar to negative pressure can appear without intrinsic dark energy. Meaning instead of creating dark energy, we create geometric conditions, making spacetime behave like dark energy. This is a bold and controversial idea. Many physicists are skeptical, calling it mathematical play without experimental evidence. But serious research groups pursue it. They don't expect to find dark energy but want to see if negative pressure properties can be activated through nonlinear curved structures, like creating propagating waves on a flat water surface. And what keeps this idea from being pure science fiction, recent numerical models show small spacetime regions, when impacted by correctly configured energy fields, can create gradients like local negative pressure regions. Not real dark energy but dark energy-like effects. Of course, these are only nanoscale simulations where equations are manageable. But if the effect is real, it could become the switch for creating warp bubble expansion without direct negative energy sources. This leads to an important realization. Dark energy may not need to be created, it only needs to be awakened, and if curvature resonance can activate dark energy-like properties locally, warp bubbles would have a firmer, more realistic footing than initial predictions. But I want to be clear, this is the edge of science. No one claims certainty, no one dares say we fully understand dark energy, because we truly don't. We only see its consequences, the universe expanding faster daily. We measure its density via cosmic microwave background. But its nature remains a mystery. Yet science always grows from such mysteries, not from easy things, but those challenging our imagination. And the combination of dark energy, an invisible universe force and warp drive, a bold human idea, brings us to the intersection of physics, philosophy, and the future. We're looking at the universe's greatest resource, but untouchable, a phenomenon pushing galaxies apart, but we don't know how to activate it in a lab. But if one day a physics team finds the right curvature resonance frequency, if they succeed in awakening local negative pressure properties, the entire concept of interstellar travel will change. Not because we create dark energy, but because we first learn to converse with spacetime's foundation. And though this is science's edge, I believe it's not fiction. This could be where the next steps of civilization begin, from the hazy darkness of theory, gradually into experimental light. And when we talk about dark energy as an invisible sea covering the entire universe, I want to take you deeper, to a level where even emptiness isn't truly empty. Because if dark energy is the macroscopic mystery, quantum vacuum is the microscopic one, where nature's strangest things happen in absolute silence. At extremely small scales, space isn't a calm, flat surface. It's a boiling sea of ceaseless quantum fluctuations. Imagine an invisible ocean where virtual particles constantly appear and disappear in fractions of a second. They arise from the uncertainty principle, borrowing energy from vacuum and returning it before the universe notices. Though extremely short-lived, these virtual particle pairs create a quantum dynamics layer, quantum foam, underlying all modern physics. And notably, these fluctuations produce the first natural negative energy effect humans ever observed. Proven through a classic experiment many of you have heard of, the Casimir effect. When you place two metal plates very close together, quantum waves between them are restricted. Outside the plates, fluctuations can occur at more wavelengths. Result: quantum pressure outside is greater than inside, and the plates are pushed closer, as if an invisible force squeezes them. This isn't theory, it's an effect measured repeatedly in labs since the 1990s with ultra-sensitive devices. It's the first proof that vacuum isn't empty. It contains energy, it can create force, it can be manipulated. But our question is bigger. Can this effect become the foundation for negative energy in warp bubbles? Some researchers believe yes, if we learn to amplify it, because the Casimir effect itself is very small. But like a guitar string resonating or a bridge vibrating at wind's right frequency, physicists think if we create suitable geometry resonance, negative energy could increase significantly. Imagine not just two flat plates, but a nanostructure with thousands of resonance cavities, each optimized to restrict quantum waves. When waves are clipped at many levels correctly, the Casimir effect doesn't just appear, it stacks, resonates, amplifies. This is ongoing research in many international labs. Japan, Germany, USA, Switzerland. They create nanocavities, quantum chambers smaller than bacteria, then measure if Casimir force increases with geometry changes. Initial results are interesting. Some groups observed force increase in fractal structured cavities. Others saw nonlinearity with superconducting materials. And a few reports, though not fully confirmed, show phenomena like Casimir resonance, meaning negative energy increases exponentially, no longer just a single effect. Of course, all still nanoscale. We can't yet create large negative energy fields impacting spacetime structure. But among all approaches, dark energy, quantum tunneling, exotic matter, Casimir vacuum fluctuation is the most controllable. You don't need a galaxy, just a clean lab, a nano-resonator set, and sensors sensitive enough to measure force variations smaller than an ant's gravity. I want to emphasize this isn't magic, not fiction, it's proven physics, just not yet scaled. Vacuum, the seeming lifeless emptiness between stars, could hold the negative energy warp drive needs. It's not far away, it's right in the room you're in air molecule gaps, electron gaps, in spacetime itself. All we need is to learn vacuum's volume knob, to resonate, amplify, gather those quantum fluctuations into purposeful structures. And if one day labs find a way to amplify Casimir millions of times, that could be the moment humanity first touches the energy form we once thought only existed in Einstein's equations. Vacuum, seemingly the emptiest place, could be the key to everything, from negative energy to warp bubbles, from dreams to reality. We've only seen its surface, only touched the quantum ocean's foam, and that ocean is deeper than our imagination dares think. And right when we start envisioning amplifying Casimir, lightly touching quantum vacuum structure, we immediately slam into another wall, not metal or energy, but mathematics. This is where many researchers admit frankly, we know the direction, but we lack the map. The reason is simple. Warp bubbles lie exactly in physics' most dangerous territory, the boundary between general relativity and quantum field theory. Both theories are correct, perfect in their domains, but they don't harmonize. GR describes space-time as an elastic fabric that can be bent. QFT describes the microscopic world as a probability storm where virtual particles fluctuate. Warp bubbles require both simultaneously, curving space-time macroscopically, but needing negative energy from microscopic quantum fluctuations. And when these equation sets meet, they rebel. Equations become high-order nonlinear, each variable affecting hundreds of others. A small metric change can collapse the entire simulation. Imagine trying to map a city, but every time you draw a house, all streets change accordingly. Every position, curvature, dimension, energy gradient reacts to everything else. This is untreatable mathematics. A chaotic dynamic system with no closed solutions, no elegant formulas, even no stable simulation way if curvature exceeds a threshold. And this leads to a strange consequence. Even with the planet's most powerful supercomputers, truly simulating a warp bubble is nearly impossible. Supercomputers can simulate a few nanometers of curvature, but a 10-meter bubble, or 1 meter, or even millimeters. No, simply beyond current computational power. The reason each tiny warp bubble part requires thousands of GR-QFT interaction calculations, and as scale increases, computation rises not quadratically or cubically, but exponentially. If simulating 10 nanometers takes days, simulating 1 millimeter would take longer than the universe's age. This makes even the most optimistic physicists admit, we're trying to solve a problem no computer is big enough for. And the problem isn't just processing power but algorithms themselves. Melvin equations, vacuum energy stress tensors, Alcubierre contraction expansion metrics, Naterio gradients, Casimir amplification, all become unstable in macro-scale simulations. When algorithms fail to converge, results aren't just wrong, they don't exist. Numerical attempts lead to divergence, values spike to infinity, drop to zero, explode in data matrices. One researcher said, simulating warp bubbles is like trying to hold water with your fingers. Adjust one parameter slightly, the whole model collapses. So what does this mean? It means currently, we can simulate warp geometry smaller than dust particles, but not a bubble large enough for a human. And this leaves scientists walking in fog. They know there's a path, but can't see more than a few steps ahead. They advance centimeter by centimeter, not because physics forbids it, but because mathematics refuses to cooperate. Part of the problem is GR and QFT aren't unified. We still lack quantum gravity, a complete toolset describing spacetime at both scales. Without a unified theory, models are patched, GR outside, QFT inside, hoping they don't break. But they always do. And today's supercomputers, capable of simulating supernovae or black hole collisions, are helpless before a 10 centimeters warp bubble. This doesn't mean warp drive is impossible. It just says we're ahead of our tools. Many historical technologies were like this. Electricity before electron theory, steam before thermodynamics, flight before aerodynamics. Same here, we've seen nanoscale warp geometry signs, we have equations, we have models, but we lack mathematics strong enough to scale them. Not yet. And this is why most warp drive remains hazy like night. Not because it's wrong, but because our tools are too weak to see clearly. We're touching the edge of a grand avenue, but light only illuminates the first few bricks. But sometimes those first few bricks are all you need to know the road truly exists. And that's why, the moment classical mathematics becomes untreatable, the physics community starts looking to a new tool. A machine not following ordinary binary logic, not bound by silicon computers' sequential rules, and most importantly, a machine operating on the very laws warp bubbles require. I'm talking about quantum computers. If classical supercomputers are giant machines for pushing equations, quantum computers can immerse in the same physical layer warp drive demands. Because every warp bubble depends on one factor, quantum vacuum structure and fluctuations. And quantum computers, unlike classical ones, don't just simulate vacuum with numbers. They can experience similar quantum states. In a classical computer, we can only simulate a few dozen virtual particles before memory explodes. But in a quantum computer, a qubit can hold multiple states simultaneously, and a qubit system can recreate complex fluctuation structures. Real vacuum foam has. This opens the first historical possibility. Simulating vacuum fluctuation models, even supercomputers can't handle. And if we can simulate vacuum, we can simulate its reaction to curved spacetime, how it generates negative energy, how it creates Casimir effects in non-existent structures. This solves one of warp drive's biggest barriers, simulating macroscopic curved field interaction with microscopic energy. That's what GR and QFT can't harmonize mathematically, but a qubit system can leap over by recreating the entire quantum environment instead of solving each equation. Many research groups now believe if any warp bubble breakthrough comes in the next 20 years, it will come unexpectedly, not from physics labs, but from ultra-cold rooms with hundreds of qubits oscillating silently. Some groups at MIT, Google, IBM have started testing small structures called mini-warp cavities, vacuum regions, with asymmetric energy gradients, potentially creating infinitesimal space-time distortions. These aren't warp bubbles yet, but first steps to see vacuum reaction when forced into unnatural configurations. We may soon try placing a metric bar, a mathematical curved structure, into a qubit system to see vacuum pattern response. If successful, we'll first simulate what classical supercomputers are completely powerless against: initial formation of an unstable warp region. Some physicists predict that at 1 million stable qubits, we could simulate full quantum vacuum of a 1-micron warp cavity. Sounds small, but let me clarify: 1 micron is large enough for curvature effects to be measurable. That would be a leap equivalent to humanity's first laser or transistor. And if micron simulation succeeds, we could adjust energy fields to produce negative gradients. If negative gradients are stably reproduced in quantum simulation, then for the first time, humans would have proof of concept for warp bubbles at real scale. Not theory, not equations, but a running model. The importance here isn't just simulation power, but how quantum computers open a new philosophy. Instead of understanding vacuum via classical math, we'll teach a quantum system to recreate vacuum for us. Instead of forcing GR and QFT harmony, qubits naturally bridge the two worlds. This is an extraordinary moment. We're witnessing cosmology, quantum science, and engineering converge for the first time. Warp drive may still be far, but the key to unlocking space-time understanding has appeared. It isn't in thrust, engines, or ships. It's in an ultra-cold chip vibrating at quantum frequencies in some lab. And when that key turns, when the first quantum simulation recreates a microscopic warp cavity, that moment will change everything. Not because we've traveled faster than light, but because for the first time, space-time becomes programmable. We won't just observe the universe, we'll start designing it. And when we talk about quantum computers, vacuum fluctuations, and structures simulatable in qubit systems, there's another quantum phenomenon I believe every audience member has heard of, an effect both beautiful and controversial, making Einstein call it spooky action at a distance: quantum entanglement. When two particles entangle, they become a unified system. No matter how far apart, 1 meter, 1 kilometer, or galaxy ends, their states remain linked. Change one particle's state, the other reacts instantly. To be clear, no information travels faster than light. This is proven, but the instantaneous correlation persists, a foundation of quantum mechanics. So why mention it for warp drive? Because at a warp bubble's boundary, time is stretched and compressed simultaneously. Quantum phenomena become extremely sensitive. If the boundary is unstable, the bubble collapses. If negative energy gradient fluctuates too much, the bubble tears. If vacuum foam oscillates out of phase, maintaining warp geometry is impossible. This leads to a bold, hypothetical but not absurd question: can entanglement synchronize warp bubble boundary regions? Imagine the boundary not a continuous surface, but thousands, millions of quantum points needing same phase, same frequency oscillation. In current metric models, tiniest asynchrony can destabilize the bubble. But if a quantum mechanism lets all boundary points connect, not for information transfer, but correlation maintenance, stability becomes far more feasible. Some physicists propose entanglement as the quantum skeleton, keeping warp bubbles from twisting or peeling under extreme curvature. This idea is still speculative, but not superstition. It's a reasonable question given vacuum's quantum nature, and every warp boundary's extreme sensitivity to microfluctuations. Some models show that creating quantum correlation fields between boundary points could cancel sporadic fluctuations via entangled states' self-correcting nature, meaning instead of controlling each boundary point traditionally, an impossible task, we let the quantum system self-regulate its stability. One research group proposed entanglement lattice, a preformed entangled pair network. When the metric field activates, entangled qubits behave as a linked system, canceling small fluctuations and keeping boundary structure more stable. Is this practical? We don't know. Current experiments only create a few hundred stable entangled pairs briefly, but for usable bubble size, we'd need millions of pairs maintained in high curvature environments, still far beyond current tech. Many physicists warn, entanglement isn't magic. It can't glue spacetime curvature like adhesive. It only provides correlation, potentially reducing quantum chaos at boundaries. But even that, if true, would be a huge advance. I emphasize this is still hypothesis. No one claims entanglement will stabilize warp bubbles, but no one rules it out, and in physics, entering GRQFT overlap regions, phenomena like entanglement aren't side effects. Sometimes they're keys. In modern cosmology models, entanglement plays a crucial role in spacetime structure. Even hypotheses that spacetime emerges from deep-level quantum entanglement networks. If true, if universe structure is built from entanglement, then using it to stabilize artificial spacetime structures isn't crazy. We're facing the big question, is there a way to make warp bubble boundaries behave like self-organizing entangled networks? And if so, would that be the start of warp bubbles, lasting longer than billionths of a second? We don't know. But what makes me optimistic, ideas once seen as bizarre, like entanglement, vacuum energy, are now experimental tools. What seems impossible today could be lab equipment in decades. Entanglement isn't the final answer, but it could be a door to how spacetime self-synchronizes at deepest levels. A door that, if we learn to open, could lead to warp bubble stability, one of physics' hardest problems. And once we've delved into entanglement as a potential mechanism stabilizing warp bubble boundaries, we must return to the bigger question many physicists see as the root problem of all space-time bending efforts: what is space-time itself made of? Because if warp drive is the art of bending the universe's fabric, we first need to understand that fabric's composition. At Einstein's scale, planets, stars, galaxies, space-time looks smooth like satin, a continuous surface without holes. But at Planck's scale, 10 circumflex 35 meters, all smoothness vanishes. At sizes dozens of orders smaller than protons, space-time isn't a flat fabric, but a quantum storm, rippling, vibrating, distorting unpredictably. Some physicists call it quantum foam, others granular spacetime. Some describe it as a network, or weave, a structure like fabric woven from deeper quantum threads. This isn't poetic metaphor. It's how many quantum gravity models describe reality's foundation. Loop quantum gravity, for example, says spacetime is built from quantum loop spin networks, knots and links creating volume and area like pixels create images. If warp drive needs to bend spacetime, then curving a small warp bubble region means what? Stretching the quantum grid itself, changing knot structure, shifting mesh eyes. And if true, warp drive isn't just an energy problem, it's about controlling reality's microstructure pattern. But another direction from M-theory offers an even bolder idea: our spacetime may be a floating brain in higher dimensional space. In this view, our 3D universe is just a slice, a thin layer in a multidimensional structure. Extra dimensions, unobservable directly because curled at Planck's size, but if they exist, they could provide shortcuts where energy moves differently, where metric structure can fold, tighten, or open in ways impossible in 3D space. Warp drive in this context could be a technique pulling or activating extra dimension geometry, like pulling a 3D carpet corner, but actually moving it in 4D space. Some M-theory models even suggest negative energy arises naturally when a brain curves along extra dimensions, meaning warp geometry may not need negative energy from our universe's vacuum, but could emerge from brain interaction with curled dimensions. But is there evidence spacetime truly has hidden structure, extra dimensions, quantum networks? Some traces from cosmology, cosmic microwave background, CMB has small anomalies, possibly remnants of topological defects, tears or seams in primordial spacetime structure. Some models predict cosmic strings galaxy-length one-dimensional threads, enormously dense, born in the universe's early phase. If cosmic strings exist, they're not just cosmological relics, they're tension threads in spacetime fabric, where curvature becomes extreme. If a warp bubble forms near a cosmic string, energy needed to bend spacetime could drop significantly. Some extreme hypotheses even suggest cosmic strings as spacetime rails, where warp fields slide like maglev trains on superconducting tracks. We haven't directly observed cosmic strings, but indirect signs, small CMB data distortions, unusual gravitational waves, keep many groups searching. If a topological defect exists, it would be direct proof space-time isn't smooth, and those tension paths could be engineered. Imagine fabric with a pulled thread. That's where you can easily bend, stretch, or fold. Same in the universe. If space-time has threads, folds, seams, warp drive could target those regions for stable lower energy bubbles. And if space-time truly is a quantum network at tiniest levels, meaning warp drive doesn't need to bend entire continuous regions, but only impact linked nodes between quantum threads. That's the difference between bending the whole net and adjusting a few knots to change the entire shape. Of course, all this remains at science's edge. We haven't observed extra dimensions, haven't measured granular space-time, haven't found cosmic strings. But strangely, every model from loop quantum gravity to M-theory to topological cosmology suggests the same space-time isn't simple. It has structure, deep layers, veins, threads, rhythm, pattern. And if warp drive is space-time bending technique, this complexity isn't a barrier, it could be opportunity. A perfect warp bubble may not need to fight the universe's fabric, it could slip through thread gaps, slide along weak seams, or pull an extra dimension for a shortcut. Perhaps we don't need to break physics laws, perhaps we just need to learn to read the universe's hidden structure and touch the right spot. And once we've discussed space-time's hidden structure, quantum threads, extra dimensions, tension paths, potentially opening warp drive opportunities, I want to bring you back to Earth, where modern physics still erects solid walls blocking our path. Because no matter how beautiful ideas are, no matter what quantum gravity models suggest, we must face an uncomfortable truth: warp drive, to become technology, must overcome nature's most fundamental limits. These limits aren't man-made, they're consequences of the universe's structure. And here are four major walls humanity can't yet cross. First wall, energy. Every warp bubble model, Alcubierre, Neterio, or variance, requires space-time distortion greater than any engine ever. Even after Harold White optimized Alcubierre, reducing from universe size to small planet size, the number remains beyond current civilization capability. Bending space-time enough for a ship isn't like starting a jet engine. It's like trying to bend an entire lake with one drop. To create that curvature gradient, energy must be not only vast, but precisely distributed in metric structure, in a boundary layer thinner than a hair. This isn't energy chargeable by batteries or chemical fuel. It involves negative energy fields, vacuum resonance, states never seen in engineering. Not coincidentally, most physicists agree, for warp drive we first need an energy revolution, a source current humanity hasn't touched. Second wall, materials. If you create a warp bubble strongly curved space-time potentially exceeding external light speed, what material surrounds the ship? Currently, no material can withstand such curvature gradients. Imagine the bubble boundary as an energy storm zone where mini-gravitational waves, quantum fluctuations, vacuum oscillations concentrate in a thin layer. Pull, compression, shear forces here, unlike any tested, even ultra-strong materials for fusion reactors, couldn't survive continuous curved fields. Some models predict ordinary matter near boundaries would decay into plasma or protons, meaning to build a warp ship, we'd need to invent non-existent materials. A metric shield layer interacting with spacetime, not just resisting mechanical force, and that's currently completely unknown. Third wall, navigation. When piloting a plane, you adjust with control surfaces, a rocket with thrust vectoring. But inside a warp bubble, you don't push the ship. You push spacetime around the ship. This leads to a strange problem. Warp bubbles don't turn left or right as expected. They move like mobile spacetime depressions, and once stabilized, direction changes can unbalance the entire structure. Current warp navigation models all face the same unsolved question: how to adjust metric curvature while keeping negative energy boundaries stable. Turn too fast, bubble collapse. Turn too slow, loss of control, or metric inertia, drift. Even braking is risky, how to stop the bubble without destructive spacetime shock. Warp navigation isn't like space navigation, it's like keeping a perfect soap bubble in a storm. Fourth wall, radiation. Warp bubble boundaries aren't just curved, They're high-energy density regions where vacuum particles can be excited, radiation can accumulate. Some models predict the ship would collect forward radiation like a giant vacuum. If the warp bubble shuts off suddenly, all that energy could release like a gamma burst. Some models warn boundaries could create shock waves, interacting with interstellar medium shocks unlike any radiation humans faced. These effects are untested but can't be ignored. We're talking uncharted physics regions, and this leads to the fifth largest wall, unknown. Unknowns, things we don't know. This is unmapped physics territory, where equations become untreatable, matter behaves unpredictably, familiar assumptions can reverse. No one knows if large warp bubbles are stable. No one knows if negative energy fields cause unwanted vacuum effects. No one knows if there's a safe limit for curvature before spacetime shifts. State, like Newton's era unknowing radiation, or Maxwell's era unknowing quantum, we may face entirely new physics layers. Warp drive forces us to explore. And I say this not to dampen optimism, but to keep our feet on the ground looking forward. Warp drive isn't myth, but neither is it tomorrow's technology. It's a journey across walls, physics set from the universe's dawn. Energy wall, materials wall, navigation wall, radiation wall, and the unknown wall. Can we cross them all? I don't know. But I believe one thing, every great civilization faces such walls, and how they confront them decides their future. If we want to reach the stars, these walls aren't barriers, they're tests. And humanity has never backed down from a big enough test. And once we've discussed the final physical walls blocking warp drive, I want to lead you to another realm. No longer technical or equations, but questions about civilization's future. Because if warp drive is truly feasible, if one day humanity finds how to bend space-time and exceed light, that technology won't just take us to stars. It will change global geopolitics, security, and cosmological ethics in ways more unpredictable than any prior invention. Start with the inevitable. Whichever nation possesses warp drive first gains absolute advantage, not just technological but existential. A nation able to move instantly between space points, reach any strategic Earth location instantly, deploy equipment or observe targets undetected. Warp drive isn't just travel, it's bending geography, erasing all distance limits. In history, distance always decided power. Sea control trade dominance, sky control modern war dominance. But controlling space-time, that's unprecedented power level. This makes national security agencies, from DARPA to Pentagon, monitor every warp clue, not from exploration dreams, but fear. If we don't lead, we'll be left behind forever. Next is warp drive risk as instant target access tool. A vehicle appearing at any coordinate without crossing airspace, no radar, no satellite warning. Like divine-level stealth aircraft, not flying, appearing. What if a warp bubble forms inside atmosphere? Worse, too near target. Warp bubbles can create strong radiation, ionize atmosphere, cause metric shocks equivalent to earthquakes on surrounding objects. This opens serious military risk. Warp weapons aren't bullets, but warp bubble side effects. If a nation accidentally or intentionally uses warp without full environmental understanding, they could cause catastrophe, not by bombs, but by tearing space-time in an area. Some models warn warp bubble strong interaction with local gravity could cause local gravitational waves. Not planet-destroying, but enough to collapse infrastructure or disrupt satellites. These risks worry policymakers until we fully understand warp drive. We don't know what we're playing with. And this isn't the most dangerous part. I want to mention another scenario. Less military, but deeper cosmological ethics. If humans possess warp drive, we'll reach other planets, worlds we don't know, have life, don't know ecosystem function. What if a warp bubble appears too near a primitive life planet? Do we accidentally destroy their environment? Because mutation radiation disrupt a young civilization? We've never faced these questions because we've never had ability beyond the solar system. But warp drive will force humanity to create cosmological ethics code, a warp treaty if you will. Because greater power brings greater responsibility, and bending space-time power is the greatest intelligence has touched. And then other risks, unpredictable ones. We know warp bubbles can accumulate radiation, but could they cause unwanted long-term vacuum effects? We know negative energy is needed, but could using it affect vacuum structure long-term? We know spacetime can curve, but is there a curvature threshold where it becomes unstable? These questions lead to what I always tell students: in science, the most dangerous thing isn't what we know, but what we don't know we don't know. Warp drive opens an unexplored land, and that land has not just starlight but shadows of unknown risks. Humanity needs caution, not from fear, but respect for universe subtlety. The universe doesn't easily yield to manipulation. It doesn't grant power to those not understanding its laws, and if warp drive becomes real, it must be developed not just with intelligence, but humility. We must remember, when you bend space-time, you're not just changing a ship's position, you're touching reality's foundation. And every mistake, however small, could carry unimaginable consequences. And once we face the risks, potential catastrophes, ethical questions hanging over humanity like cold stars, I want to bring you to another vision, one not gloomy or threatening but vast, full of promise. Because though warp drive holds dangers, it also opens a door unprecedented in human history, the interstellar era. Imagine centuries from now, when warp bubbles are stable, negative energy controlled, humans no longer imprisoned in the light prison, will no longer be a civilization locked in the solar system. We'll become the first Earth species to cross interstellar boundaries. A warp fleet leaves Earth, and hours later reaches Alpha Centauri system. Days later, Tau Ceti. Weeks later, dozens of new worlds. Not centuries, not millennia. Weeks from a civilization's view, that's not just progress, it's total transformation, a rebirth. As first worlds are reached, interstellar colonies form, atmospherically suitable planets become new homes. Harsher ones, super-Earths or ice worlds, become research centers or industrial bases. And as humanity spreads to many worlds, we no longer face extinction risk from single events. No asteroids, climate change, wars. That alone makes warp drive the greatest turning point in life history. But more, accessing billions of tons of resources in other systems' asteroid belts. Interstellar economy will explode unimaginably. Precious metals, helium-3, natural superconductors, clean water ice, even compounds unknown on Earth, all within reach. If you think industrial or digital revolutions change the world, interstellar economy will be exponential of all combined. A civilization exploiting hundreds of systems simultaneously, no longer limited by one planet's resources. This brings us to a famous scale, Kardashev. Currently, humanity is 0.7, not fully controlling Earth's energy. With warp drive, we'll quickly reach Type I, controlling all planetary energy. Then, with systems part of economy, toward Type II, using entire star energy, building megastructures like Dyson swarms, reshaping interstellar environments. You see, warp drive doesn't just open physical doors, it opens civilization doors, a star-traveling civilization no longer bound by old limits. We'll have science centers on older planets studying universe history, floating cities on giant gas oceans, telescopes in completely dark, unpolluted space. And perhaps, somewhere in the Milky Way, we'll find other life traces. Not via weak century-delayed radio signals, but direct foot on distant worlds, turning rocks, analyzing ice samples, touching surfaces of planets possibly once or currently hosting life. That will change not just science, but humanity's self-perception in the universe. And then, with interstellar cities, warp transport routes, knowledge exchange networks between systems, our civilization itself will transform. Humans living in different gravities, climates, day-night cycles, culture, language, art, philosophy, all branching, diversifying unpredictably. Perhaps, after thousands of years, humanity becomes a family of many branches, all tracing to Earth but adapted to their planets. But the most beautiful, every branch will look back at this moment, when warp drive was just a hazy idea, and know that's where the interstellar journey began. And no matter how distant that future, whether needing decades or centuries of research, Warp drive remains the light illuminating humanity's greatest potential, escaping limits and exploring beyond sight. A civilization only becomes great when daring to step out of its own shadow. And warp drive is that step, the step opening the universe. And once we've painted a vast interstellar future vision, where humanity steps out of Earth's cradle, becoming star-dwelling species, something natural happens, big questions emerge. Questions modern science, however powerful, often avoids. Not because too dangerous, but too vast, too deep, touching where knowledge and imagination intersect. And in such moments, I always feel returning to the universe's philosophical view, what I believe is science's most important essence, asking questions, even without answers yet. First question, if warp drive is feasible, has any other civilization built it before us? The universe is 13.8 billion years old. Earth only 4.5 billion. Our recorded civilization, just 6,000 years. The gap between us and universe age is so large it almost forces the question, if warp drive is a natural tech civilization step, has someone exceeded light before humans knew fire? And if so, where are they? Where did they go? What traces did they leave? This is the Fermi paradox in a new version. Not where are aliens? But if warp drive feasible, why isn't the universe full of their signals? Maybe they don't want to be found. Maybe they've evolved beyond material forms we recognize. Or maybe warp drive isn't as easy as we think. It's a door only opening for civilizations passing tests most fail. Second question, is warp drive a natural step for every mature civilization? Looking at human development, some tech milestones seem inevitable. Tools, steam, electricity, information, quantum. These shifts aren't choices. They're consequences of exploring reality's nature. So some argue warp drive is that type, an unavoidable step when a civilization hits light speed limit and must find ways past. In this model, every sufficiently advanced civilization eventually learns space-time control. If true, the universe could be full of space-time works we don't recognize because operating on completely different principles from ordinary matter. Or warp drive may not be natural, but a rare branch only very special civilizations pursue. Because it requires three extremely hard, simultaneous achievements: intelligence, energy, and long-term survival. Most civilizations likely self-destruct before reaching warp drive. And we, tiny creatures on a blue planet, may be among the few continuing the walk. Third question, perhaps deepest. Does the universe want us to exceed its limits? One strange thing, everything about warp drive, from dark energy, vacuum fluctuations, quantum space-time structure, to metric bending ability, has been in the universe from the beginning. Nothing needs invention, only correct understanding. Like a game with pre-written rules, players just need enough smarts to discover shortcuts. When I look at Einstein's equations, M-theory models, vacuum fluctuation experiments, I can't help wondering, is warp drive part of the universe from the start? Is the universe designed so sufficiently intelligent beings can learn to fold space-time and go beyond light? If so, warp drive isn't just technology, it's proof intelligence can unlock reality's structure. And this leads to the final question no civilization can avoid. If light is matter's limit, where is intelligence's limit? Warp drive challenges physical limits, but it also challenges how we think about ourselves. A civilization bending space-time no longer limited to universe resident role. It becomes participant in universe structure. And that's not a small step, it's a fundamental knowledge shift. Science hasn't answered these questions. Maybe 500 more years needed. Maybe never definitive answers. But for me, the important thing isn't answers. It's daring to ask, because that's what distinguishes a stagnant civilization from one reaching for stars. And if warp drive truly is that door, today's questions will become tomorrow's map for a future where human intelligence doesn't just look at the universe but steps into it. And as unanswered questions still echo, as we face both awe and humility before the universe's scale, I want to bring everything back to reality. Humanity's actual progress in the race to open the 10 times light speed door. Honestly, we don't have warp drive yet. No large-scale negative energy, no materials withstanding warp boundaries, no unified GRQFT algorithms. But we have things humanity never had before. Nanoscale space-time curvature signals from Harold White experiments. increasingly stable, smoother Netareo simulations yearly, stronger nano-Casimir cavities, first quantum computers simulating vacuum dynamics, and a scientific community from NASA to private labs, expanding exponentially. No large warp bubbles yet, but small warp geometries. No warp engines, but warp math running femtoseconds. No interstellar ships, but a generation of scientists seeing warp drive not as fiction but long-term goal. And why do we need it? Not just curiosity, not just wanting to know what's at Alpha Centauri, not just dreaming of interstellar civilization. We need warp drive because humanity's future depends on not being confined to one planet. Every single world civilization is vulnerable to extinction from asteroids, wars, pandemics, global warming, or natural and self-made mistakes. Warp drive isn't just a star door, it's a civilization's escape hatch wanting to outlive its parent star. Space-time is the final wall, and warp drive is the first tool with potential to cross it. So what happens in the next 10 years? Perhaps quantum models simulating stable micron-scale warp cavities. Perhaps a research group reproducing thousand-fold Casimir resonance. Perhaps NASA announcing first metric engineering program. In 50 years, maybe we'll build devices creating measurable negative energy gradients, bending visible small space-time regions. Labs will use 7th or 8th generation superconductors for millimeter-scale Netareo field rings. Quantum computers will simulate warp bubbles large enough for a chip. And perhaps a prototype warp engine, not a ship, but test chamber, will activate for billionths of a second, creating curvature signals recorded by hundreds of sensors. In 100 years, no one knows. But imagine, a ship traveling not by chemical fuel but space-time bending. It doesn't accelerate, it stays still in flat interior while outside universe moves. That ship could leave Earth orbit, jump to Proxima Centauri in hours, TRAPPIST system in days, beginning an era where each star system becomes a city, each galaxy a continent, every distance a choice not a limit. And when that happens, humanity will no longer ask how to exceed light. We'll ask where first, to the turquoise ocean planet in Epsilon Eridani, purple forest world in Kepler 452, or completely empty regions where light has never been recorded. Warp drive doesn't just change how we travel, it changes how we view the universe. From a dark, distant, cold ocean, it becomes accessible, understandable, belongable. And when first footsteps touch stars, they'll carry the question following humans since dawn: who are we in this universe? A question only interstellar travel can answer. And finally, standing before the warp door, opening 10 times light speed, bending our own destiny, I want to leave you one question. A simple question carrying all future weight. If this journey's first chapter has been this wondrous, what do you think the next chapter, when we truly open the warp door, will look like? If you want to continue unlocking universe mysteries with me, please subscribe so you don't miss any journey. And if these stories touch your curiosity, leave a follow so we meet again in the next part of our interstellar voyage.